Okay, we are now at section 6.2, non-uniform circular motion. This should be a short um, discussion. The net force exerted on the particle is the vector sum of the radial force and the tangential force. Now, earlier, the section we just talked about, there was only one force, and that was the radial force inward. Uh, and it was caused by the tension in the spring. It can also be caused by uh, gravitational force. We'll learn later in when you get to E and M, that'll be next semester. There's a magnetic force acting on a charged particle moving in a uniform magnetic field that causes it to travel in a circular motion. And there's the electric force acting on an electron in orbit around a nucleus in the Bohr model of the hydrogen atom. That's chapter 41. That's in the Bohr model. I mean, we're not talking about probability clouds there. We're talking about just a model. But um, here we're talking about both a radial force inward, directed inward, and a um, tangential force outward. So that the total acceleration will be the radial acceleration, which is the centripetal acceleration, and the radial acceleration. In other words, if there's something causing the ball to change its speed the tangential speed, then there's a radial acceleration. So the sum of the forces, the total force is equal to the sum of the forces in the radial direction and the sum of the forces in the tangential direction. Um, so that's non-uniform circular motion. Uniform circular motion meaning that the object going around in a circle maintains its speed. Um, and we'll learn when we get to Kepler's laws that there is a change in speed because of the elliptical orbits. But I'm jumping the gun there. We won't discuss that right now. Let's look at a little quiz. A bead slides at constant speed along constant speed. That's key. A bead slides at constant speed along a curved wire lying on a horizontal surface, as shown in the figure. Draw the vectors. Uh, draw the vectors representing the force exerted by the wire on the bead. Well, along here, the wire is going to provide a centripetal force directed downward. Well, actually, I already I didn't mean to jump the gun, but I did. So you have a centripetal force. Actually, all along here, you'll have a force directed inward on this curve. There is no force at B, and then at C you have a force directed upwards, and uh, so that's what's causing the force. Draw the vectors representing the force exerted by the wire. Those are the forces that the wire exerts um, on the little bead. Now, a bead, it really shouldn't say constant speed because then it. Uh, let's see. Did I? Oh, yeah. Okay, here it is. I'm sorry. Um, a bead slides at constant speed along a curved wire lying on a horizontal surface as shown in the figure. Now, suppose the bead speeds up with constant tangential acceleration as it moves toward the right. Draw the vectors representing the force on the bead at points A, B, and C. Well, at A, you had the centripetal force downward, but this time you have a force that's causing it to speed up. So now you're going to have a tangential force. Um, so the total force is going to be the sum of the radial force and the tangential force at A, and then also at C. You can see the tangential force is going horizontally, the radial force, the centripetal force is going upward, and the sum of the forces is at an angle going this way. And I believe that's it for this short section. Just whenever there is a tangential component of force and acceleration, you will get a sum of the forces It's not all just radial. There will be a force that is the vector sum of the radial force and the tangential force. Okay, let's